Okay, so now we're moving to R. And as you can see here, I have actually 3 of the datasets that we're going to use already loaded. So basically D is the data from the Get Out the Vote experiment that we already talked about last week. So I have already loaded because it takes a couple of minutes basically to load. I also have the DS1 sample, which was the sample removing all the phones, all the observations where the phones were enlisted. And basically then I have a D sample, which is also on the code for this class that you can see it. It basically just takes a random sample of the entire data to work a little bit easier with matching. So matching has a lot of advantages, but because it's a bit more of a heavy computing process, a lot of the times with such large samples, like over 2 million or things like that, it works quite slow. And because I'm going to be coding live, I don't want you to be looking at this and get super bored just waiting for code to run, okay? So again, it's the same sample that's on the code, so you can actually just load them and start from there. The first thing that I wanted to talk about a little bit, though, that is related to the our last class with RCTs, is the fact of whether you have to include or not include covariates. And we're going to see it both with the matching and also with randomized controlled trials. So I want to talk a little bit in the context of randomized controlled trials before getting into the matching idea. So what I'm going to do basically here is just run a model, okay? The typical LM robust that we have, just for the simple regression, only with the treatment and the strata variable, as we saw last class, but without covariates, okay? So remember that the outcome that we're interested in is whether the person voted or not in 2002, and we had the variable that was treatment real. That was the one that was assigned randomly, and then we needed to also control by strata, right? Because remember that it was randomized at by each stratum. Okay, great. So then I just say that my data will be DS1, and I run this, and as you can see here, we can see that, takes 1 second, we can see that we get actually an effect of intention to treat, okay? So in this case, if I intend to treat or contact a household with a Get Out of the Vote phone call, then the effect on voting is 0.15%, okay? That's very, very low. But as you can see also, the t-stat is very low and the p-value is quite high, okay? Basically, that means that we can't reject the fact that this effect is actually 0. What happens now if I include covariates? Remember that covariates in this case are not necessary because I randomized, okay? So in expectation, this covariates should be balanced, and also by construction, the treatment assignment is not related to these other variables. So they're not confounders, really, if the randomization process was done correctly. So what do I gain when I add covariates? So let me add some covariates. In this case, I'm going to add the number of people that are in the house. I'm going to add whether they voted in 2000 and they voted on 98. I'm also going to add whether they are new registered, and their age, and whether they're females. Female, okay. And I run exactly the same thing. So what should we expect in this? Remember that these are not, the covariates that I just added are not confounders under the assumptions of randomization, and also should not be related to the treatment, right? So as you can see here, the point estimate is quite similar to a certain extent to the one that we got without without covariates, and that is good. Okay, you should not expect your point estimate to change when you add covariates. If it changes too much, then basically it means that your randomization was not done correctly. So in this case, it doesn't change that much. That's great. But if you look at the standard error, for instance, you can see that the standard error actually goes down when you include covariates, and your t-stat goes up, which means that your p-value is going to go down. Okay, so that means basically that even though your point estimate did not change considerably, and that is something that you should expect because, again, randomization, these are not confounders, it does help reduce a little bit the variance of your estimator, of your estimate in this case. So in this first regression, for instance, we were explaining probably very little of the model, right? As you can see, our R squared, okay, this the adjusted R squared is 0.01, which again is very low. This means basically that the treatment and the strata are not really capturing a lot of the variance of that voting behavior. However, when we add all these other variables, you can see that our adjusted R squared jumps up a lot, and now we're explaining over 25% of, or it's not exactly the percentage of a variation that we're explaining, but it's sort of proportional to that. So we're explaining much more of the variation of the voting behavior than in the previous model. Okay, so because our model is fitting the data better in that sense, and it's capturing more of that variation, that means that my estimate in this case, it's going to be more precise. So again, it's going to be centered, or it should be centered in the same true value of the treatment effect, but now my sampling variance, it's going to be reduced in that sense. So you should never run just the version with covariates, just for you to have in mind. If you're presenting something, you should always run both, and always keep an eye of the fact that your point estimate should not change that much. It should always be kept sort of in the same, around the same magnitude. Okay, after that brief intermission, now we're gonna move on to matching. So in this case, for matching, we're gonna use the Match-It library, which is a great package basically because it collects a lot of the matching methods that we're going to be seeing. So in one package, you can actually implement a lot of different matching strategies. So as you can see here, and it's very useful always to just do a question mark and the name of the function that you want, basically because you can see here all the different arguments that you have and that you can actually use. So let's do the first one. We're gonna match, and I'm gonna assign it to an object name M1 in this case, and I'm gonna do match it. And in this case, we need a formula for our treatment, okay? I'm assuming in this case that we're not working with a randomized, with an experimental data. I'm assuming that we're working with observational data. So in this case, I'm gonna leave out the treatment assignment. We did not run an experiment, for instance, and I'm just seeing data from a Get Out the Vote campaign. So basically, I'm seeing data from people that were contacted versus people that were not contacted. So now our treatment, the one that we're interested in, is whether that household was contacted or not. So I'm going to try to model whether a household was contacted or not by using the covariates that we have, okay? So in this case, I'm gonna use strata again because it combines both state and competitiveness. I'm gonna see whether there's one or two people that vote in that household. I'm gonna also use their voting history and whether they're a new registered voter, age, and again female, including all the variables that I already had, right? And in this case, my data is gonna be the sample, okay? I could run it with the other whole sample. It just takes a long time because it has a lot of observations, okay? So I'm gonna run the smaller version. The method in this case, I'm just gonna do a nearest neighbor matching, but as you can see, you can have different methods. And I wanna do exact matching, in this case, by strata. So again, I think that strata is a variable that it needs to be very closely matched. So not only match an expectation, but actually want two units that come from the same state and from the same district in terms of competitiveness. So I'm going to match exactly on straight up. And then basically what this is going to do is build my propensity score in this case, because if you see here, the default is doing a propensity score, running a generalized linear model with a logit link. And it's going to match on that, okay? So if you can see here, you can actually change the distance measure. So we're saying by default it's a generalized linear model with a logit link, but you can also use a Mahalanobis distance, for instance. So if instead of what we're running here, you also included the argument distance and you just wrote down Mahalanobis, it would run the same thing, but instead of using the propensity score, it would use the Mahalanobis. And I'll leave that up to you to compare basically how both of them behave, okay? So we're just waiting. This takes like a little bit, even though it's not that many observations. For some reason, matching even with this greedy algorithm is not the most efficient thing out there. Okay, great. So now I have M1 here, and as you can see, I can maybe take this down a bit. If you open it up, you can see some of the objects that you get out here. So you have a matching matrix, you have a subclassification, you have some weights, you have the model that you fitted. So a lot of these things we're not going to be using, but some of them are useful. So the first thing that I do want to see, actually, is my matching matrix. So let's see how this looks like. So as you can see, we have some row numbers here, and then we have a string of characters right here. Basically, this are the indices for the treatment units, and these are the matched control units. So for instance, for unit 17187, we have that it matched the control unit 1638. For the unit 17188, it matched the control unit 1171. One important thing to remember here, and please remember this, by default, this gives an ATT at best. So basically what I'm saying is that usually you have a smaller treatment group than a control group. In most observational studies, you have a larger control sample than a treatment sample. So what matching does in this case is takes the treatment group, which is the smallest one, and tries to find units in the control group that are similar to that. So basically what you're doing is try to find a smaller group in the control group that has similar characteristics to the treatment group. So again, we're matching on the treatment group characteristics. So in that sense, we are going to be getting an average treatment effect on the treated. And that's important to have in mind when you're analyzing this. Okay, so this looks like this, but how can we use this? So basically what I'm gonna do is generate a vector of treatment IDs or treatment indices. And basically this is the names of the rows here. So what I'm gonna do is take the row names of the matching matrix, but that will generate a character vector, okay? Because they're names. So what I just do is transform it as numeric, okay? So I can run that. As you can see, I get basically these numbers. Awesome. Then I do the same, but with the control IDs, and I do the same as numeric, because again, this vector is actually characters. So I just take M1 matching, and I take the first column. In this case, it only has one column because we're only doing pairwise matching, so 1 to 1. But you could eventually find more than one match for a unit, for a treatment unit. You could find 2, 3, however much you want. It helps a little bit with power in the sense that it increases your sample, but it doesn't buy much in other sense. Okay, so let's do our control units. Let's just see how it looks like. And great, everything looks good. Again, always do those little checks. just to make sure that you're doing everything right. It's very easy to mess up in certain extent, and it's just easier that every time that you run something, just do like a little check to just to visually inspect that everything seems okay. Okay, so now I'm gonna generate my match sample, which will basically be my D sample for the treatment unit. So basically I'm selecting just the treatment units here. And then I'm gonna add row, and I'm gonna say add the rows that have the control units, okay? And that should be fine. One important thing to do this, instead of, for instance, just doing contact equal 1, for example, is that in this case, we're matching all units, all treatment units. But for instance, we can be a little more restrictive and say like, don't match everyone. And for instance, match everyone that is at a 0.1, that has a control unit that is at most a 0.1 standard deviation away. So in that sense, if you put what it's called a caliper, which again is a restriction on how far away your matches can be, that may end up with a smaller sample that's not necessarily the whole treatment sample. Okay, you might lose certain treatment units, and you'll certainly lose certain control units, and that will make your sample smaller, but again, better matched and better balanced in that sense. So caliper is a good argument to use, and again, you should play with it to see how it behaves, whether it changes something or not. Maybe it doesn't if they're very overlapped with each other, but if they're not, caliper can generate big differences in that sense. Okay, so let's add that row, and we have DM1 now. Oh, yes, because I put it on the column, which was a mistake, of course. I'm selecting rows, so I'm sorry, that was my bad. Okay. Now we're good. Okay, DM1 now, then it's my match sample. So as you can see, I have the same sort of variables from the D sample, but let's see about the treatment. You should expect here, if you're doing one-to-one matching, that you have the same amount of units in the treatment and the control group. So let's just check that that is right. So as you can see that it's right, I have a little bit over 5,000 in the control group and a little bit over 5,000 in the treatment group. Great. It seems that this worked fine. One important thing is, how do we analyze this? So first, we want to check balance. So for balance, what I'm going to do is first generate a matrix of covariates. So basically what I'm going to do is just select covariates. So, sorry. And I'm going to select the covariates that I want, which are basically these, right? I'm not going to select straight up because it's a factor, and it will basically ruin my mean tab, but you can also select it and transform it into dummy variables. That's totally fine. So I'm going to just do that. Sorry. Basically, I just have a data frame with covariates, and then I'm just going to do mean tab. Remember that you pass first the covariates, then you pass the treatment variable, and then where the treatment is 1, and then where the treatment is 0. And let's see how this is balanced. Okay, great. As you can see here, again, both groups seem very balanced. Okay, the difference are almost 0 in standard deviations for most of them. P-values are super high, which means basically that there's no significant differences between both groups in this covariance. Awesome. So it seems that propensity score matching worked fine for this. But remember that I'm having a smaller sample in that sense. Awesome. So how do we actually analyze this? So there's two ways that we can do so. The first one, we could do a t-test, and I'll leave this up to you, where basically we can do the outcome for the people that are in the treatment group, and the outcome that are for the people in the control group, and I use paired equal true. So as you can see, I find almost a 4% difference in this case. What happens if I compare it, for instance, to just the regular model? Let's see, LM robust. Now we're doing vote 02, but now instead of regressing it on the treatment, we're doing it on the contact, right? And let me just put summary here so we get the standard errors and everything. We're gonna run that. And we're gonna run also, while that is running, exactly the same thing, but now we're gonna use our matched data, okay? So remember that this had, D sample had a lot of, DS1 had over almost 2 million observations. And as you can see, the value for contact is 0.06. Now I'm gonna run the same, but with my matched sample. So remember that now I only have a little bit over 10,000 observations. And let's see how that goes. So as you can see, we have a value of 3.7, okay? Why are those two things different? This is an important thing. In both of them, basically, we are trying to get the effect of being contacted on voting. But here we're assuming, basically, because we're not using any sort of covariates, only strata, we're assuming that conditional strata contact was basically random, which might not be the case, right? In the second one, however, in the matching one, we are already controlling by those confounding, but controlling in a very flexible way, in the sense that we matched units that looked very much like each other, okay? So what happens now if I add all the other covariates? Let's add all these other covariates to the regular regression. What happens here? So remember that originally was 0.62, but again, this is assuming unconfoundedness only on strata, which might be a huge stretch, right? And now when I add all the covariates, which would be more similar to what we were doing with matching, I get a much smaller estimate, and in this case is 2.8%, okay? Which is closer to the realm here of what matching did, which is 3.7. Again, they're different because we're matching differently. This is using extrapolation, we're using a much bigger sample, while this is matching more closely for covariates, and again, using a much smaller sample in that sense. So all those things matter to a certain extent. We could also do the same thing instead of, for instance, matching. We could do subclassification, okay? So that's something that you should do too. But in this case, basically, you can't use the exact argument. So you can't match exactly on strata. So maybe one thing that you could do if you wanted to match exactly by strata and still do subclassification is just do a loop using the different strata and doing subclassification within each strata. Okay, I'll leave this up to you, but basically you can do also this and run the subclassification in this case with changing just the method, the method function, and seeing whether it affects your balance or not, which one is better. Great, let's go back now to our slides.